Hi, I'm Stephanie Guthrie.
And I'm Natasha Shaybani.
We're here to discuss polymers and tissue engineering. So, tissue engineering has the goal of regenerating, repairing, and replacing damaged tissues in the body.
Myth or fact, there is no distinction between tissue-engineered constructs and pure biomaterials.
I think that's true because both are used to help with healing in the human body. Isn't tissue engineering just a fancier term for material in the human body?
Well, though tissue-engineered constructs incorporate biomaterials, they are not one and the same. Tissue engineering exploits cells and other small biological molecules to better emulate the properties of native human tissues.
Myth or fact? The three main classes of biomaterials are ceramics, metals, and polymers. Polymers are most often used to create a scaffold in tissue engineering.
I'm thinking that's a fact.
So polymers are a great choice of material because there are so many to choose from with highly tunable properties. Some are soft and some are hard, and they can come from a variety of sources. Natural polymers are derived from biological sources, whereas synthetic polymers are fabricated in a lab.
Myth or fact, the best material for tissue-engineered constructs is one that will not degrade in the body.
I guess that's true because degradation can release a lot of dangerous chemicals.
Myth. There are certain polymers that can degrade safely in the body, which is obviously ideal since we want new native tissue to replace the construct. TE constructs can have vastly different properties depending on what tissue they are replacing or what disease state the native tissue is in. For instance, think of the difference between bone and skin. There are other properties that we consider, such as immune response, porosity, and stiffness.
Alright, here's an easy one. Tissue engineering is a complex problem, and researchers are doing a fantastic job approaching the challenge.
That's definitely a fact.
Yeah. So here are a few examples of what's going on in the field of tissue engineering. As you can see, researchers are working on applications for the whole body: heart tissue repair, neural regeneration, skin grafting, and much more. This is an exciting field with so much more to be discovered.
So now let's put this into more perspective by reviewing a specific case study from University of Michigan. In order to circumvent the risk of heart failure following mitral valve damage, researchers cast a polymer mold and embedded myofibroblasts into a tissue-engineered construct that could be sewn back into the heart as a valve replacement.
Alright, myth or fact? Tissue-engineered products go straight from the lab bench to the bedside, and they don't have to be screened for safety or efficacy.
That's a myth. There's no way they would let something in the body without making sure that it's safe first.
Good job. The primary concern in engineering is always safety, so that's why it's important for us to have regulatory agencies like the FDA that will make sure that researchers are being responsible with their research and that the products will benefit society.
Thanks for watching.